All right, let's dive right in. Today, we're looking at a really clever piece of tech called the Prime Collective Communications Library, or PCCL for short. Now, this thing is designed to tackle one of the biggest and honestly one of the messiest problems in AI right now. How in the world do you get the entire world to help train a single massive AI model?
So, yeah, that's the central question, isn't it? How do you train one giant AI model when the computers doing all the heavy lifting are literally all over the planet, connected by nothing more than the regular old public internet? It sounds kind of straightforward, but trust me, this is an incredibly tough nut to crack.
And here's why it's so hard. You see, the traditional way we train AI is in what's called a high-performance computing cluster. Just picture a perfectly clean, controlled lab. Everything is stable, all the machines are in the same room, and the network is ridiculously fast. But the public internet? It is the complete opposite. It's wild, it's chaotic, it's unpredictable. Connections drop, speeds are all over the place, it's a mess. And that gets us to the heart of the challenge. The software libraries we've been using for years, like NVIDIA's NCCL, they're fantastic inside that perfect little HPC lab, but they were never, ever built for the chaos of the open internet. They just assume that no machine will ever fail or that some new computer won't just decide to join the party halfway through. On the internet, that assumption, it just breaks instantly. And this is where our hero enters the story. It's called PCCL, the Prime Collective Communications Library. And what's so cool about it is that it was built from the ground up with one goal in mind, to not just survive, but to actually thrive in the messy, chaotic world of the public internet. Okay, so how does it actually pull this off? How does PCCL manage to get all these computers spread across the globe to play nice and work together? Let's get into the mechanics, because this is where it gets really interesting. It all starts with a really simple but powerful structure, a master-client model. So you've got this one computer, the master, and its job is to act like an air traffic controller. It's not actually moving the data itself, but it's the one coordinating everything, telling all the other computers, the clients, what to do, when to talk, and who to listen to. It's the orchestra conductor. Now check this out. PCCL has this super elegant way of dealing with new machines that want to join in. It's not a free-for-all. First, the new computer has to register with the master. Then, and this is the cool part, the computers that are already working have to take a vote on whether to let the new guy in. Only if they all agree is the new peer brought into the fold. This totally prevents a random new machine from crashing the whole operation. And that whole voting thing, it's part of a bigger idea they call micro-consensus. This is really the secret sauce. It means that for every single important step, like letting a new peer in or starting the next round of math, every single machine has to give a thumbs up. It makes sure everyone is perfectly in sync, moving in lockstep. And if one machine happens to fail or just drops off the network, everybody knows about it instantly. No confusion. But, being tough and reliable is only half the battle. You also have to be fast. Really fast. And this is where PCCL pulls out its next big trick, making communication across these huge distances not just possible, but incredibly efficient. I mean, just look at this map. If you're sending data from, say, Oregon to Germany, it's not just a straight line. The actual path it takes through all the internet's cables and routers makes a huge difference. The shortest path physically is almost never the fastest one. What you really want is the path with the most bandwidth, the biggest data pipe you can find. So how does PCCL find that magic route? Well, it treats the whole thing like a famous puzzle in computer science, the traveling salesman problem. It is constantly measuring the connection speed between all the computers and calculating the absolute most efficient loop for the data to make to visit every single node. It's not about geography, it's about pure, raw data speed. And the results? They are just, staggering. In their tests running between data centers in Western Europe, this method hit a peak bandwidth of 45 gigabits per second. That is an insane amount of data to be moving across the public internet for a single training job. So how do they hit a number that high? Well, instead of just using a single connection between 2 points, which tops out at around 3.6 gigabits per second here, they just open up tons of connections at the same time, in parallel. It's like opening up more lanes on a highway. And as you can see on the chart, once they hit about 128 parallel connections, boom, they've maxed out the link at that incredible 45 gigabit per second speed. And when you stack it up against a more traditional library, something like Glue, you can really see the benefit of all this smart network planning. In a North American test, PCCL was more than 6% faster, and across the tighter European network, it was over 14% faster. I mean, that's a huge speed up that you get just from choosing a smarter path for your data.
So PCCL is great at fixing the network problem. But what if you could also, I don't know, fix the algorithm itself so it doesn't have to be so chatty all the time? Well, that's the next layer of genius here, using training methods that just don't need to communicate as much.
See, standard training methods like DDP are super high maintenance. After every single little baby step of work, all the computers have to stop, get on the phone, and sync up. But these other algorithms, like one called Diloco, which PCCL is built for, they're way more chill. They let each computer just go off and do its own thing for a while, and they only check in once in a while to share what they've learned. And then there's Async Deloco, which takes it to a whole other level. Instead of that stop and start approach of work, then communicate, then work, it does both at the same time. While the GPUs are busy crunching the numbers for the next step, the results from the last step are being sent around in the background. This quote from the paper just says it all perfectly. The communication overhead is effectively hidden behind local compute. It's like doing your homework on the bus ride to school. You're using that travel time for something productive, so the trip feels like it takes no time at all. That's exactly what's happening here. So what's the big takeaway from all this? It's simple. Your incredibly expensive, incredibly powerful GPUs are always doing what you paid them to do: compute. They are not just sitting around twiddling their thumbs waiting for some slow network to deliver the next bit of data. This just maximizes your efficiency and saves a boatload of time and money. And when you put all this together, it unlocks some seriously powerful new ideas. You could train models on those cheap, spare spot instances from cloud companies. You know, the ones that can vanish without warning. You could build these monster AI systems that span across Amazon, Google, and Microsoft's clouds. At the end of the day, this is how we start to build a much more resilient and truly global infrastructure for AI. Which really just leaves us with one final and pretty mind-bending question. If this kind of technology means that pretty much any computer anywhere on Earth can chip in and reliably help train the next generation of AI, what kinds of massive problems are we going to be able to solve next? That is a very exciting thought.